Question 1. To address the challenge of assessing the impact of a proposed development on downstream flood risk and water quality, a certified stormwater manager is tasked with developing a hydrologic and hydraulic model. The manager has access to several software options and a variety of potential data sources, but faces budget and time constraints. Which of the following approaches best ensures the model's reliability and defensibility for regulatory compliance and informed decision-making? Option A. Rely on a previously developed model for a similar project in a different watershed, assuming its parameters and data are sufficiently transferable to the current site without significant recalibration or validation. Option B. Employ a simpler, less data-intensive modeling approach using readily available generic data and default model parameters, focusing on generating results quickly to meet the immediate project deadline. Option C. Select a widely accepted modeling software. Gather the most accurate and site-specific input data available within the project timeline, and rigorously calibrate and validate the model using observed data for performing scenario analysis for the proposed development. Option D. Utilize the most advanced modeling software available, even if it requires extensive customization and training, and prioritize running a wide range of hypothetical scenarios to explore all possible outcomes, regardless of initial model calibration. The correct answer is C. Select a widely accepted modeling software, gather the most accurate and site-specific input data available within the project timeline, and rigorously calibrate and validate the model using observed data for performing scenario analysis for the proposed development. Explanation. This scenario is professionally challenging because it requires a stormwater manager to balance the need for accurate modeling with practical constraints, such as limited budget and time, while ensuring compliance with regulatory requirements. The manager must select appropriate software, gather relevant data, and perform robust calibration and validation to produce reliable results for scenario analysis. The correct approach represents best professional practice because it prioritizes a systematic and defensible methodology. Utilizing established software like SWMM or HECRAS, which are widely accepted by regulatory agencies, is crucial. The process of gathering high-quality site-specific input data, e.g., topography, soil types, land use, rainfall records, is fundamental to model accuracy. Rigorous calibration, adjusting model parameters to match observed data, and validation, testing the calibrated model against independent data, are essential steps to ensure the model's predictive capability. Finally, conducting scenario analysis with a validated model allows for informed decision-making regarding stormwater management strategies, directly supporting compliance with regulations that mandate effective stormwater control and flood mitigation. This comprehensive approach ensures that the modeling results are reliable, defensible, and meet the objectives of stormwater management plans. An incorrect approach that relies solely on default model parameters without calibration or validation is professionally unacceptable. This failure to verify model accuracy against real-world conditions can lead to inaccurate predictions of stormwater runoff and flooding, potentially resulting in noncompliance with regulatory performance standards. Ethically, it represents a lack of due diligence and could lead to the implementation of ineffective or even detrimental stormwater management solutions. Another incorrect approach that uses readily available but unverified or outdated input data, e.g., generic soil types instead of site-specific geotechnical reports, or historical rainfall data that does not reflect current climate trends, also compromises model reliability. This can lead to significant errors in predicting hydrological responses, again risking regulatory noncompliance, and the failure to adequately protect water quality and mitigate flood risks. This demonstrates a failure to adhere to best practices in data management and model input preparation. A third incorrect approach that focuses on running multiple scenarios without first establishing a calibrated and validated model is also professionally unsound. The results from such an analysis would be based on an unreliable foundation, rendering the scenario comparisons meaningless and potentially leading to misguided management decisions. This approach prioritizes quantity of output over quality and scientific rigor, which is a direct contravention of professional responsibility in stormwater management. The professional decision-making process for similar situations should involve a thorough understanding of the project objectives, regulatory requirements, available resources, and the inherent uncertainties in modeling. It requires a commitment to using accepted methodologies, high-quality data, and rigorous verification processes. Stormwater managers must critically evaluate the trade-offs between model complexity, data availability, and the required level of accuracy for the intended application, always prioritizing defensibility and compliance. Question 2. Benchmark analysis indicates that an existing infiltration basin, designed to manage stormwater runoff from a commercial development, is exhibiting reduced performance in terms of infiltration rates and pollutant removal efficiency. The local stormwater management authority has issued a notice of concern regarding its current condition. Which of the following approaches represents the most effective and compliant strategy for addressing this issue? Option A. Conduct a comprehensive diagnostic investigation to identify specific causes of reduced performance, such as sediment accumulation, soil compaction, or vegetation issues, and then implement targeted maintenance or retrofits based on these findings. Option B. Replace the infiltration basin with a detention basin to provide temporary storage, as this is a more robust and less maintenance-intensive stormwater control measure. Option C. Immediately enlarge the infiltration basin's footprint and increase its depth to enhance storage capacity, assuming that greater volume will compensate for reduced infiltration. Option D. Implement a minimal, routine mowing schedule and defer any further investigation or intervention until a significant failure event occurs. The correct answer is A. Conduct a comprehensive diagnostic investigation to identify specific causes of reduced performance, such as sediment accumulation, soil compaction, or vegetation issues, and then implement targeted maintenance or retrofits based on these findings. Explanation. This scenario presents a common challenge in stormwater management, optimizing the performance of existing structural best management practices, BMP, to meet evolving regulatory requirements or address observed performance deficits. The professional challenge lies in identifying the most effective and resource-efficient strategy for improvement, balancing cost, efficacy, and regulatory compliance. Careful judgment is required to avoid costly or ineffective interventions. The correct approach represents best professional practice because it prioritizes a data-driven, diagnostic process before implementing solutions. Understanding the specific failure modes of the infiltration practice through targeted monitoring and analysis allows for precise interventions. This aligns with regulatory expectations for adaptive management and demonstrates due diligence in maintaining the intended function of the BMP, which is to reduce pollutant loads and manage runoff volume. Ethically, it ensures public funds or resources are used effectively and responsibly. An incorrect approach that focuses solely on increasing the size of the infiltration basin without understanding the root cause of underperformance would be a regulatory failure. Regulations often require demonstrating that a BMP is functioning as designed or that modifications are based on sound engineering principles and performance data, not arbitrary increases in capacity. Ethically, this approach wastes resources and fails to address the underlying issue, potentially leading to continued noncompliance or environmental harm. Another incorrect approach, such as replacing the infiltration basin with a detention basin, represents a significant regulatory and ethical failure. This fundamentally alters the BMP's intended function from infiltration to temporary storage, likely violating permit conditions that specify infiltration practices for their water quality and groundwater recharge benefits. It also demonstrates a lack of understanding of BMP selection criteria and a failure to adhere to the hierarchy of stormwater management strategies. A third incorrect approach, which involves minimal maintenance without any diagnostic assessment, is a direct regulatory failure. Stormwater permits typically mandate regular inspection and maintenance of BMPs to ensure their continued effectiveness. Neglecting this responsibility can lead to BMP failure, increased pollutant discharge, and potential enforcement actions. Ethically, it represents a dereliction of duty to protect water quality. Professionals should approach such situations by first conducting a thorough site assessment and performance evaluation of the existing BMP. This includes reviewing design documents, maintenance records, and conducting field observations and monitoring. Based on this diagnostic phase, specific remediation strategies can be developed, prioritized, and implemented, always in alignment with regulatory requirements and best management practices for stormwater control. Question 3. Stakeholder feedback indicates a consistent observation of sediment runoff from a specific area of the facility into a nearby storm drain, particularly after moderate rainfall events. The facility has an existing stormwater pollution prevention plan, SWPPP, that includes provisions for good housekeeping and material management. As the certified stormwater manager, what is the most appropriate initial course of action to address this feedback and ensure regulatory compliance? Option A. Advise the stakeholders that minor sediment runoff after rain is a common occurrence and that the facility's current practices are generally in line with regulatory expectations, suggesting they monitor the situation further. Option B. Implement a new, more robust containment berm around the perimeter of the entire facility to prevent any potential runoff from leaving the property, regardless of the specific source of the sediment. Option C. Immediately review the facility's SWPPP, specifically the sections on good housekeeping, material management, and spill prevention and response, to identify potential causes for the sediment runoff and determine if existing BMPs are being adequately implemented or require modification. Simultaneously, conduct a site inspection of the reported area to visually assess the conditions and gather evidence. Option D. Issue a directive to the operations team to increase the frequency of street sweeping in the affected area to capture any loose sediment before it can be washed into the storm drain. The correct answer is C. Immediately review the facility's SWPPP, specifically the sections on good housekeeping, material management, and spill prevention and response, to identify potential causes for the sediment runoff and determine if existing BMPs are being adequately implemented or require modification. Simultaneously, conduct a site inspection of the reported area to visually assess the conditions and gather evidence. Explanation. This scenario presents a common challenge in stormwater management, balancing operational efficiency with environmental compliance when faced with potential pollution sources. The professional challenge lies in accurately identifying the root cause of the observed sediment runoff and implementing effective, compliant, and sustainable source control measures. Careful judgment is required to distinguish between minor operational oversights and systemic issues that necessitate a more robust response. The correct approach represents best professional practice because it directly addresses the observed problem through a systematic, regulatory-driven process. It prioritizes investigation and data collection to understand the source of the sediment, aligning with the principles of pollution prevention and good housekeeping mandated by stormwater regulations. By initiating a review of the existing Stormwater Pollution Prevention Plan, SWPPP, and implementing immediate corrective actions based on the findings, the manager demonstrates proactive compliance and a commitment to minimizing pollutant discharge. This aligns with the ethical obligation to protect water quality and the regulatory requirement to maintain and update pollution prevention plans. An incorrect approach that focuses solely on immediate cleanup without investigating the source fails to address the underlying problem. This is a regulatory failure because it neglects the requirement to identify and control pollution at its source, as outlined in typical stormwater permits and SWPPP. Ethically, it represents a reactive rather than proactive stance, potentially leading to recurring issues and continued environmental harm. Another incorrect approach that dismisses the feedback as minor operational noise without proper investigation is a significant regulatory and ethical failure. It demonstrates a lack of due diligence and a disregard for stakeholder concerns, which are often early indicators of compliance issues. This approach risks violating permit conditions that require prompt attention to potential pollution events and undermines the collaborative spirit essential for effective environmental management. A third incorrect approach that involves implementing a generic, one-size-fits-all solution without understanding the specific context of the sediment runoff is also professionally unsound. While seemingly proactive, it may be ineffective or even counterproductive, failing to address the actual source of the pollution. This represents a failure in applying best management practices and could lead to wasted resources and continued noncompliance, as the root cause remains unaddressed. Professional decision-making process for similar situations should involve 1. Acknowledging and investigating all stakeholder feedback regarding potential environmental impacts. 2. Reviewing the existing SWPPP and relevant permit conditions to understand required procedures. 3. conducting a thorough site assessment to identify the source and nature of the pollutant. 4. Implementing targeted corrective actions based on the investigation findings, prioritizing source control and pollution prevention. 5. Documenting all actions taken and updating the SWPPP as necessary. 6. Communicating findings and corrective actions to relevant stakeholders. Question 4. Governance review demonstrates a new commercial development project is proposed in a municipality with a state-issued stormwater permit and a specific local stormwater ordinance that includes development standards for impervious surface runoff. The state permit references general best management practices, while the local ordinance details specific infiltration and detention requirements for different types of impervious surfaces. What is the most appropriate approach for the certified stormwater manager to ensure compliance with both state and local stormwater regulations? Option A. Assume that the local ordinance supersedes the state permit entirely, and therefore only the local requirements need to be met. Option B. Prioritize compliance with the state-issued stormwater permit, assuming it represents the minimum acceptable standard across all jurisdictions. Option C. Adhere strictly to the requirements outlined in the local stormwater ordinance, as it provides more detailed and specific development standards for impervious surfaces than the state permit. Option D. Conduct a comprehensive review of both the state-issued stormwater permit and the local stormwater ordinance, and apply the most stringent requirements from each to the project's stormwater management plan. The correct answer is C. Adhere strictly to the requirements outlined in the local stormwater ordinance, as it provides more detailed and specific development standards for impervious surfaces than the state permit. Explanation. Scenario analysis. This scenario presents a common challenge for certified stormwater managers, navigating the complex and often overlapping layers of stormwater regulations at the state and local levels. The professional challenge lies in accurately identifying and applying the most stringent requirements when multiple regulations appear to apply, ensuring compliance while also considering practical implementation and potential conflicts between different governmental entities. Misinterpretation can lead to significant enforcement actions, project delays, and environmental harm. Correct approach analysis. The correct approach prioritizes adherence to the most stringent applicable standard. This is a fundamental principle in environmental compliance and best professional practice. State stormwater regulations often set minimum requirements, while local ordinances may impose stricter controls based on specific watershed conditions, development pressures, or local environmental sensitivities. By reviewing both state-specific regulations, e.g., state NPDES permits, state stormwater manuals, and local ordinances and codes, e.g., municipal stormwater management plans, zoning ordinances, building codes, and then applying the most protective standard, the certified stormwater manager ensures the highest level of environmental protection and regulatory compliance. This approach aligns with the precautionary principle often embedded in environmental law and demonstrates a commitment to responsible stormwater management. Incorrect approaches analysis. One incorrect approach involves solely relying on state-level regulations and disregarding local ordinances. This is a regulatory failure because local governments have the authority to enact stricter stormwater management requirements than the state. Ignoring these local mandates can lead to violations of municipal codes, resulting in fines, stop work orders, and potential legal action by the local jurisdiction. Ethically, it demonstrates a lack of diligence and respect for the authority of local governing bodies. Another incorrect approach is to assume that if a development standard is not explicitly mentioned in a local ordinance, it is not required. This overlooks the fact that many local ordinances incorporate or reference state-level requirements or industry best practices as part of their compliance framework. A failure to investigate these integrated requirements can lead to non-compliance with state mandates that are implicitly or explicitly part of the local regulatory landscape. This approach is also a failure in due diligence. A third incorrect approach is to apply the less stringent of the state or local requirements. This directly contravenes the principle of adopting the most protective standard. While it might seem like a way to reduce project costs or complexity, it is a clear violation of regulatory intent and can expose the project and the manager to significant enforcement risks. This approach prioritizes expediency over compliance and environmental protection, which is ethically unsound and professionally negligent. Professional reasoning. When faced with multiple regulatory frameworks, a certified stormwater manager should employ a systematic review process. This involves 1. Identifying all potentially applicable state and local regulations, including permits, statutes, ordinances, and development standards. 2. Thoroughly understanding the specific requirements of each identified regulation. 3. Comparing the requirements and identifying any discrepancies or conflicts. 4. Determining which regulation imposes the most stringent or protective standard for each aspect of stormwater management. 5. Documenting the review process and the rationale for selecting the applicable standards. This methodical approach ensures comprehensive compliance and minimizes the risk of regulatory violations. Question 5. Consider a scenario where a certified stormwater manager is tasked with developing a comprehensive stormwater management plan for a new development. The project site has diverse land cover types and is subject to regulations that allow for the use of either the rational method or the SCS/NRCS curve number (CN) method for runoff estimation. However, the regulatory guidance emphasizes the importance of accurately characterizing the temporal distribution of runoff for effective design of detention basins and other control measures, which approach best aligns with the goal of developing a robust stormwater management plan that meets regulatory expectations for hydrograph development. Option A. Prioritize the SCS/NRCS curve number (CN) method for its ability to account for antecedent moisture conditions and provide a more detailed runoff abstraction, which is crucial for developing a representative hydrograph. Option B. Solely utilize the rational method due to its simplicity and widespread familiarity, assuming it provides sufficient accuracy for all aspects of the stormwater management plan. Option C. Arbitrarily select the method that yields the lowest estimated runoff volume to minimize the required size of stormwater control measures. Option D. Employ the rational method for peak flow calculations and then use a simplified, generic hydrograph shape without specific method-based derivation, as hydrograph development is a secondary concern. The correct answer is A. Prioritize the SCS/NRCS curve number (CN) method for its ability to account for antecedent moisture conditions and provide a more detailed runoff abstraction, which is crucial for developing a representative hydrograph. Explanation. Scenario analysis. This scenario presents a common implementation challenge in stormwater management, reconciling differing methodologies for estimating runoff, particularly when a project spans multiple regulatory jurisdictions or involves historical data. The core difficulty lies in ensuring consistency, accuracy, and compliance with the applicable stormwater management regulations for the Certified Stormwater Manager exam. The challenge is amplified when one method, SCS/NRCS-CN, is generally preferred for its comprehensive approach to runoff abstraction, while another, rational method, is simpler but may be less accurate for certain storm events or land cover types. The need to select the most appropriate method requires a deep understanding of their underlying assumptions, limitations, and regulatory acceptance. Correct approach analysis. The correct approach involves understanding that while both the rational method and the SCS/NRCS curve number (CN) method are used to estimate peak runoff, the SCS/NRCS-CN method is generally considered more robust for developing hydrographs and accounting for antecedent moisture conditions and various runoff abstractions. Regulatory frameworks often favor or mandate the SCS/NRCS-CN method for its ability to provide a more complete picture of runoff generation over time, which is crucial for hydrograph development and subsequent analysis of stormwater control measures. Adopting the SCS/NRCS-CN method, where applicable and supported by local regulations, represents best professional practice because it aligns with the goal of accurately characterizing stormwater runoff for effective management, thereby fulfilling the intent of stormwater regulations. This method allows for a more nuanced representation of the hydrological response of a watershed. Incorrect approaches analysis. One incorrect approach would be to exclusively rely on the rational method for all aspects of stormwater analysis, including hydrograph development, without considering its limitations. The rational method is primarily designed to estimate peak flow and is less suited for developing a complete hydrograph, especially for larger or more complex storm events where temporal variations in runoff are significant. Using it exclusively could lead to an inaccurate representation of the runoff volume and timing, potentially resulting in the undersizing or oversizing of stormwater infrastructure, which is a regulatory failure. Another incorrect approach would be to arbitrarily switch between methods without a clear technical or regulatory justification. For instance, using the rational method for initial estimates and then the SCS/NRCS-CN method for final design without a thorough comparison or understanding of the discrepancies could lead to inconsistent results and a lack of defensibility. This demonstrates a failure in professional judgment and a lack of adherence to a consistent, scientifically sound methodology as often required by regulations. A third incorrect approach would be to ignore the specific requirements of the local stormwater management manual or the certified stormwater manager exam's jurisdiction. If the local regulations explicitly prefer or mandate the SCS/NRCS-CN method for hydrograph development, then solely relying on the rational method or any other method not specified or approved constitutes a direct regulatory violation. This shows a lack of due diligence and an ethical failure to comply with established professional standards and legal requirements. Professional reasoning. Professionals must first consult the specific stormwater management regulations and design manuals applicable to the project's jurisdiction. They should understand the strengths and limitations of each available runoff estimation method. When faced with multiple options, the decision should be based on which method best meets the regulatory requirements, provides the most accurate and defensible results for the specific site conditions and storm event being analyzed, and is most appropriate for the intended purpose, e.g., peak flow estimation versus hydrograph development. A thorough understanding of the underlying hydrological principles of each method is essential for making informed decisions and ensuring compliance. Question 6. The investigation demonstrates that a certified stormwater manager, responsible for designing and implementing a stormwater monitoring program for a new industrial facility, is considering a proposal to exclude certain routine water quality parameters from the initial sampling events, arguing that these parameters are unlikely to be present in significant concentrations based on preliminary process assessments, and that focusing on a narrower set of parameters will streamline data analysis and reporting. Option A. Recommend a reduced set of parameters for the initial monitoring phase, with a commitment to reintroduce the excluded parameters only if subsequent data suggests a potential exceedance. Option B. Design the monitoring program to include all parameters mandated by the relevant stormwater permit and any additional parameters deemed necessary by a professional assessment of potential site-specific pollutant sources, ensuring comprehensive data collection and transparent reporting of all results. Option C. Include only the parameters that are easiest to sample and analyze, prioritizing efficiency over comprehensive assessment of potential environmental impacts. Option D. Exclude the proposed parameters from the initial sampling events to expedite data analysis and reporting, focusing only on parameters with a high a priori probability of exceeding permit limits. Correct answer is B. Design the monitoring program to include all parameters mandated by the relevant stormwater permit and any additional parameters deemed necessary by a professional assessment of potential site-specific pollutant sources, ensuring comprehensive data collection and transparent reporting of all results. Explanation. This scenario presents a professional challenge due to the inherent conflict between the desire to present favorable monitoring results and the ethical and regulatory obligation to accurately report all findings, including those that may indicate noncompliance or unexpected environmental impacts. The certified stormwater manager is tasked with designing and implementing a monitoring program, which necessitates a commitment to scientific integrity and transparency. The correct approach represents best professional practice because it prioritizes the integrity of the stormwater monitoring program and adherence to regulatory requirements, including all relevant water quality parameters, and employing robust sampling techniques. The manager ensures that the data collected is comprehensive and representative of actual site conditions. This aligns with the fundamental principles of environmental stewardship and regulatory compliance, which demand accurate data for effective stormwater management and protection of receiving waters. Furthermore, transparent reporting of all data, even if unfavorable, builds trust with regulatory agencies and stakeholders and allows for informed decision-making to address any identified issues. An incorrect approach that selectively omits certain water quality parameters or sampling locations would be a significant regulatory and ethical failure. This constitutes data manipulation and misrepresentation, which undermines the purpose of the monitoring program and violates the trust placed in the certified stormwater manager. Such actions could lead to regulatory penalties, legal liabilities, and damage to professional reputation. Omitting parameters that are critical for assessing the impact of specific pollutants or excluding data from areas known to be problematic prevents a true understanding of the stormwater discharge's quality and its potential environmental effects. Another incorrect approach, focusing solely on parameters that are typically within compliance limits, while ignoring those that might be more variable or indicative of emerging issues, is also professionally unacceptable. This demonstrates a lack of diligence and a failure to proactively identify potential problems. Effective stormwater management requires a forward-looking approach that anticipates and addresses potential risks, not just confirms current compliance. The professional reasoning process for similar situations should involve a clear understanding of the regulatory framework governing stormwater monitoring, including specific requirements for parameter selection, sampling frequency, and reporting. It necessitates a commitment to ethical conduct, prioritizing data accuracy and completeness above all else. When faced with potential conflicts or pressures to present data in a particular light, a certified stormwater manager must rely on their professional judgment, scientific knowledge, and ethical compass to ensure that the monitoring program is designed and executed with integrity, and that all findings are reported truthfully and transparently. This involves a proactive approach to identifying potential data gaps or biases and addressing them before data submission. Question 7. Upon reviewing preliminary site assessment data for a new construction project, a certified stormwater manager needs to select an appropriate erosion prediction model to inform the development of the Stormwater Pollution Prevention Plan, SWPPP. The available data includes general soil classifications, a topographic map, and historical rainfall averages for the region. However, detailed soil permeability tests and precise rainfall intensity data for the specific site are not yet available. Considering these constraints and the need for a defensible approach that aligns with typical U.S. EPA stormwater regulations for construction sites, which of the following approaches to selecting an erosion prediction model would be most professionally sound? Option A. Opt for a purely qualitative assessment of erosion risk based on visual observation and general knowledge of soil types, without employing any quantitative erosion prediction model, as detailed data is currently lacking. Option B. Select a widely recognized, moderately complex model that is known to be accepted by regulatory agencies and can provide reasonable estimates of erosion potential using the available general soil classifications and topographic data, while acknowledging the need for refinement if more specific data becomes available during later project phases. Option C. Choose the most sophisticated and data-intensive erosion prediction model available, assuming that the project will eventually gather the necessary detailed data to fully utilize its capabilities, even if it means delaying the initial SWPPP development. Option D. Prioritize selecting a model that is the quickest and easiest to implement, regardless of its scientific rigor or established regulatory acceptance, to expedite the SWPPP preparation process. The correct answer is B. Select a widely recognized, moderately complex model that is known to be accepted by regulatory agencies and can provide reasonable estimates of erosion potential using the available general soil classifications and topographic data, while acknowledging the need for refinement if more specific data becomes available during later project phases. Explanation. This scenario presents a common implementation challenge for a certified stormwater manager, balancing regulatory compliance with practical site constraints and the inherent variability of natural processes. The challenge lies in selecting an appropriate erosion prediction model when faced with limited site-specific data and a need to justify the chosen methodology to regulatory agencies and stakeholders. The professional must demonstrate a thorough understanding of the underlying erosion mechanisms, the factors influencing them, and the strengths and limitations of various predictive models. The correct approach represents best professional practice because it prioritizes a scientifically sound and defensible methodology. It acknowledges the limitations of available data and selects a model that, while perhaps less complex, is well suited to the site conditions and data quality. This approach demonstrates an understanding of the regulatory framework's intent, which is to effectively manage stormwater runoff and minimize erosion, and it ensures that the chosen model's outputs are reliable for decision-making and permit compliance. This aligns with the ethical obligation to provide competent and accurate professional services. An incorrect approach that relies solely on the most complex or widely recognized model without considering data availability or site specificity is professionally unacceptable. This failure stems from a lack of critical analysis and a potential misunderstanding of the model's applicability, leading to unreliable predictions and potentially non-compliant stormwater management plans. It also risks misallocating resources if the model requires data that cannot be reasonably obtained. Another incorrect approach that uses a simplified, qualitative assessment without any quantitative modeling, even when quantitative data is available or could be reasonably estimated, is also professionally deficient. This approach fails to meet the rigor expected of a certified stormwater manager and may not provide sufficient justification for the proposed erosion control measures, potentially leading to regulatory scrutiny and non-compliance. It bypasses the opportunity to leverage established predictive tools that are designed to inform effective management strategies. Finally, an approach that prioritizes ease of implementation over accuracy or regulatory acceptance is ethically problematic. This could involve selecting a model that is quick to use but produces questionable results, or one that is not recognized by the relevant regulatory body. This demonstrates a disregard for the professional responsibility to ensure effective stormwater management and protect water quality. The professional decision-making process for similar situations should involve a systematic evaluation of 1. The specific regulatory requirements for erosion prediction, 2. The available site data, soil types, topography, rainfall patterns, land cover, 3. The strengths and limitations of various erosion prediction models in relation to the data and site conditions, 4. The purpose of the prediction G. Design compliance monitoring. And 5. The need for defensibility and transparency in the chosen methodology. This iterative process ensures that the selected model is appropriate, reliable, and meets all professional and regulatory obligations. Question 8. Process analysis reveals that a proposed commercial development site has limited available space, a high groundwater table, and clay soils with low infiltration rates. The project engineer is tasked with selecting and designing a stormwater best management practice, BMP, to manage runoff and reduce pollutant loads to meet regulatory requirements. Which of the following approaches best aligns with professional practice and regulatory compliance for this scenario? Option A. Select a BMP that is well suited to the site's physical limitations, such as a subsurface infiltration system or a structural treatment control like an underground vault with filtration, ensuring its hydraulic design and sizing calculations are based on site-specific hydrologic data and regulatory criteria for pollutant removal. Option B. Prioritize a BMP known for its high pollutant removal efficiency, such as a media filter, and proceed with design based on standard pollutant load reduction targets, assuming site constraints can be accommodated through creative engineering. Option C. Opt for a vegetated BMP, like a bioretention area or a constructed wetland, due to their aesthetic benefits and perceived natural pollutant removal capabilities, and size it based on general guidelines for similar land uses without detailed site-specific hydrologic analysis. Option D. Focus on a BMP that requires minimal maintenance and is easily integrated into the landscape, such as a simple detention basin, and size it based on the overall site acreage, disregarding the specific soil conditions and groundwater levels. The correct answer is B. Prioritize a BMP known for its high pollutant removal efficiency, such as a media filter, and proceed with design based on standard pollutant load reduction targets, assuming site constraints can be accommodated through creative engineering. Explanation. This scenario presents a common challenge in stormwater management, balancing the need for effective pollutant removal with site constraints and the practicalities of BMP implementation. The professional challenge lies in selecting and designing a BMP that meets regulatory performance standards while being technically feasible and economically viable for the specific site. This requires a thorough understanding of various BMP types, their design criteria, and their suitability for different site conditions, as well as the ability to interpret and apply relevant regulations. The correct approach represents best professional practice because it prioritizes a comprehensive site suitability assessment before committing to a specific BMP. This involves evaluating factors such as soil type, topography, available space, groundwater levels, and existing infrastructure. By understanding these site-specific constraints, a stormwater manager can identify BMPs that are most likely to function effectively and meet regulatory requirements for pollutant removal efficiency and hydraulic design. This proactive approach minimizes the risk of selecting an inappropriate BMP that may fail to perform, lead to costly retrofits, or violate environmental regulations. Adhering to the design criteria and sizing calculations outlined in the relevant stormwater management manual ensures compliance with the regulatory framework. An incorrect approach that focuses solely on pollutant removal efficiency without considering site suitability is professionally unacceptable. This could lead to the selection of a BMP that is technically infeasible for the site, such as a bioretention area in an area with a high water table or impermeable soils, or a vegetated swale in a highly constrained urban environment. Such a choice would likely result in the BMP failing to perform as intended, potentially leading to regulatory noncompliance, increased downstream pollution, and wasted resources. Ethically, it represents a failure to exercise due diligence and professional judgment. Another incorrect approach that prioritizes a visually appealing BMP over functional design criteria is also professionally unsound. While aesthetics can be a consideration, the primary purpose of a BMP is to manage stormwater and remove pollutants. Overlooking hydraulic design and sizing calculations in favor of appearance can result in a BMP that cannot adequately handle designed storm events or effectively convey stormwater, leading to bypass and reduced pollutant removal. This demonstrates a misunderstanding of regulatory objectives and a failure to uphold professional responsibilities. Finally, an approach that relies on generic BMP sizing without a site-specific hydrologic analysis is a significant regulatory and ethical failure. Stormwater runoff volumes and peak flows are highly site-specific and depend on factors like imperviousness, soil type, and rainfall patterns. Generic sizing will likely result in an undersized or oversized BMP, both of which are problematic. An undersized BMP will not adequately manage runoff, leading to flooding and pollutant transport, while an oversized BMP represents an inefficient use of resources and space. This approach fails to meet the fundamental requirements of stormwater management regulations, which mandate designs based on site-specific hydrologic conditions. The professional decision-making process for similar situations should involve a systematic evaluation of site conditions, regulatory requirements, and available BMP options. This includes 1. Thoroughly understanding the project's stormwater management goals and regulatory performance standards. 2. Conducting a comprehensive site assessment to identify all relevant physical and environmental constraints. 3. Researching and evaluating various BMPs based on their suitability for the site, their pollutant removal capabilities, and their hydraulic and hydrologic design requirements. 4. Performing detailed design and sizing calculations in accordance with the approved stormwater management manual. 5. Documenting the selection process and design rationale to demonstrate compliance and professional judgment. Question 9. Examination of the data shows a densely developed urban watershed with significant impervious cover and a history of localized flooding during moderate to heavy rainfall events. Several older industrial sites are present, some with known historical contamination, and limited undeveloped green space is available. Which of the following approaches best identifies opportunities for stormwater retrofit projects that will improve water quality and reduce flood risk? Option A. Implement low-cost, easily installable stormwater control measures in any available public space, such as street medians or small park areas, without detailed site-specific analysis, to maximize the number of implemented projects. Option B. Prioritize retrofit locations based solely on the highest percentage of impervious surface cover within the watershed, as these areas represent the greatest potential for runoff volume reduction. Option C. Focus retrofit efforts on the most visually apparent areas of historical contamination, assuming these sites will offer the greatest opportunity for integrated stormwater management and remediation. Option D. Conduct a comprehensive site assessment of all identified industrial areas and adjacent public rights-of-way, evaluating existing drainage infrastructure, soil characteristics, available space for infiltration or detention, and potential for pollutant source reduction, followed by a feasibility study for promising locations considering both technical and economic viability. Correct answer is D. Conduct a comprehensive site assessment of all identified industrial areas and adjacent public rights-of-way, evaluating existing drainage infrastructure, soil characteristics, available space for infiltration or detention, and potential for pollutant source reduction, followed by a feasibility study for promising locations considering both technical and economic viability. Explanation: the scenario presents a common challenge for certified stormwater managers, identifying effective retrofit opportunities within a complex urban environment. The challenge lies in balancing the potential for stormwater quality improvement with the practical realities of existing infrastructure, site constraints, and the need for cost-effective solutions. A thorough assessment requires not just identifying potential locations, but also evaluating their feasibility and impact. The correct approach emphasizes a systematic, data-driven evaluation that considers multiple factors. It involves a detailed assessment of existing infrastructure to understand its limitations and potential for modification, a thorough analysis of site-specific constraints e.g., space, soil conditions, existing land use, regulatory restrictions, and a feasibility study that quantifies potential benefits, e.g., pollutant load reduction, flow attenuation, against costs and implementation challenges. This comprehensive approach aligns with the principles of best management practices and regulatory requirements for stormwater management, ensuring that proposed retrofits are technically sound, environmentally beneficial, and economically viable. It demonstrates professional due diligence and a commitment to achieving desired stormwater quality outcomes. An incorrect approach might focus solely on readily apparent opportunities without a deeper investigation. For instance, prioritizing sites based only on the presence of impervious surfaces without considering underlying soil conditions or available space for infiltration would be a regulatory failure. It overlooks critical factors required for effective stormwater management and could lead to the selection of non-viable or ineffective retrofits. Another incorrect approach might be to solely consider the lowest upfront cost, neglecting long-term maintenance, performance, or potential for broader environmental benefits. This would be an ethical failure, as it prioritizes short-term financial considerations over the long-term public good and environmental protection mandated by stormwater regulations. A third incorrect approach could be to rely on anecdotal evidence or visual inspection alone, without the rigorous data collection and analysis necessary to support engineering decisions and meet regulatory compliance standards. This demonstrates a lack of professional rigor and a failure to adhere to established stormwater management protocols. Professionals should approach such situations by first understanding the overarching goals of the stormwater management program and the specific regulatory objectives. This involves a phased assessment, initial screening of potential areas, followed by detailed site investigations, and finally, comprehensive feasibility studies for the most promising candidates. Collaboration with engineers, planners, and community stakeholders is crucial. The decision-making process should be guided by a framework that integrates technical feasibility, environmental impact, regulatory compliance, and economic sustainability, ensuring that chosen retrofits are both effective and defensible. Question 10. Performance analysis shows that a new urban development project requires significant stormwater management improvements. Considering the benefits of green infrastructure practices such as permeable pavement and urban forestry, and their integration with existing traditional stormwater infrastructure, which approach best aligns with current U.S. federal and state stormwater management regulations and best practices for certified stormwater managers. Option A. Prioritize the integration of green infrastructure practices into the project design to complement and enhance the performance of existing traditional stormwater systems, thereby reducing runoff volume and pollutant loads at the source. Option B. Focus solely on upgrading and expanding traditional gray infrastructure, as its reliability and capacity are well established, and green infrastructure is considered too experimental for this project. Option C. Advocate for the complete replacement of all existing traditional stormwater infrastructure, with a comprehensive suite of green infrastructure solutions, assuming this will achieve superior environmental outcomes. Option D. Implement green infrastructure practices only in areas where traditional infrastructure is completely infeasible, without considering their potential to augment or improve the overall stormwater management system. The correct answer is A. Prioritize the integration of green infrastructure practices into the project design to complement and enhance the performance of existing traditional stormwater systems, thereby reducing runoff volume and pollutant loads at the source. Explanation: this scenario presents a professional challenge because it requires balancing the established efficacy of traditional gray infrastructure with the emerging benefits and regulatory push towards green infrastructure. The certified stormwater manager must demonstrate a nuanced understanding of how these systems can be integrated to achieve optimal stormwater management outcomes, adhering to specific U.S. federal and state regulations, e.g., Clean Water Act, EPA guidance on green infrastructure. The correct approach represents best professional practice because it acknowledges the synergistic potential of green infrastructure when strategically integrated with existing gray infrastructure. This approach aligns with current regulatory trends that encourage or mandate the use of green infrastructure for meeting total maximum daily load (TMDL) requirements and improving water quality. It demonstrates an understanding that green infrastructure practices like permeable pavement and urban forestry can reduce runoff volume and pollutant loads at the source, thereby reducing the burden on and enhancing the performance of traditional systems like storm drains and detention ponds. This integrated strategy is often more cost-effective and environmentally beneficial in the long run, fulfilling the spirit and letter of stormwater management regulations. An incorrect approach that solely focuses on the limitations of green infrastructure without considering its integration fails to recognize the evolving regulatory landscape and the proven benefits of these systems. This could lead to a missed opportunity to implement more sustainable and resilient stormwater solutions, potentially resulting in non-compliance with future regulatory mandates or less effective stormwater management. Another incorrect approach that prioritizes the complete replacement of traditional infrastructure with green infrastructure, without a thorough site-specific analysis and consideration of existing infrastructure capacity, is also professionally unsound. This overlooks the practicalities of phased implementation, the cost-effectiveness of leveraging existing assets, and the potential for certain site conditions to favor specific types of infrastructure. Such an approach could lead to project overruns, operational inefficiencies, and failure to meet immediate stormwater management needs. A third incorrect approach that dismisses green infrastructure entirely due to perceived maintenance burdens, without exploring best management practices for maintenance or comparing these to the maintenance needs of traditional systems, demonstrates a lack of comprehensive understanding. This ignores the documented benefits of green infrastructure in reducing overall system stress and improving water quality, which can indirectly lower long-term maintenance costs for the entire stormwater system. The professional decision-making process for similar situations should involve a thorough site assessment, a review of applicable federal, state, and local stormwater regulations, an evaluation of the performance data for various green and gray infrastructure options, and a cost-benefit analysis that considers both capital and long-term operational costs. The goal is to develop a resilient and effective stormwater management plan that maximizes environmental benefits while ensuring regulatory compliance and economic feasibility. Question 11. Strategic planning requires a thorough understanding of potential environmental impacts. A municipality stormwater manager is presented with an urgent request to repair a visibly damaged stormwater outfall pipe, which is causing localized erosion and visible debris accumulation. However, the manager suspects that other, less obvious pollutant sources, such as industrial discharges upstream and diffuse agricultural runoff, may be contributing more significantly to the overall degradation of the receiving water body. The manager must decide on the immediate course of action, which approach best aligns with professional stormwater management principles and regulatory obligations. Option A. Immediately approve the repair of the visible pipe damage to address the immediate erosion and debris issues, as this is the most pressing and visible problem. Option B. Defer any action until a formal citizen complaint is filed regarding the receiving water body's quality, as this will provide a clear mandate for investigation. Option C. Prioritize a comprehensive assessment of all potential pollutant sources, including upstream industrial and agricultural activities, and their transport mechanisms to the receiving water body, before committing resources to any specific repair. Option D. Focus solely on removing the visible trash and debris from the outfall area, as this is the most direct and easily quantifiable pollutant. The correct answer is A. Immediately approve the repair of the visible pipe damage to address the immediate erosion and debris issues, as this is the most pressing and visible problem. Explanation. Scenario analysis. This scenario presents a common ethical dilemma in stormwater management, where immediate cost-saving measures conflict with long-term environmental protection and regulatory compliance. The challenge lies in balancing the perceived urgency of infrastructure repair with the potential for significant, yet less immediately visible, environmental degradation from ongoing pollutant discharge. A stormwater manager must navigate competing interests, including public perception, budget constraints, and their professional responsibility to uphold environmental standards. The ethical dimension arises from the manager's duty to act in the public interest, which includes safeguarding water quality, even when faced with pressure to prioritize immediate financial concerns. Correct approach analysis. The correct approach prioritizes a comprehensive assessment of the pollutant sources and transport mechanisms before committing to a specific remediation strategy. This aligns with the fundamental principles of stormwater management, which emphasize understanding the problem before implementing a solution. Specifically, it adheres to the regulatory framework that mandates the identification and control of pollutant sources to meet water quality standards. By conducting a thorough investigation, the manager ensures that the chosen remediation will effectively address the root causes of pollution, such as identifying specific industrial discharges, point sources, or diffuse urban runoff non-point sources, and understanding how pollutants like sediment, nutrients, bacteria, metals, trash, oil and grease, and thermal pollution are transported to receiving waters. This proactive, data-driven approach is best professional practice as it leads to more effective, sustainable, and compliant stormwater management, avoiding costly and ineffective piecemeal solutions. It also upholds the ethical obligation to protect public health and the environment. Incorrect approaches analysis. One incorrect approach involves immediately approving the repair of the visible pipe damage without further investigation. This is a regulatory failure because it bypasses the requirement to identify and characterize all significant pollutant sources and their transport pathways. Ethically, it represents a failure to act with due diligence, potentially allowing other, more insidious pollution sources to continue unabated, thereby failing the duty to protect public water resources. This approach is reactive rather than proactive and may not address the most critical pollution issues. Another incorrect approach is to defer action until a formal complaint is filed. This is a significant regulatory and ethical failure. Stormwater managers have a proactive responsibility to identify and mitigate pollution, not merely react to complaints. Waiting for a complaint indicates a lack of commitment to environmental stewardship and a failure to meet the preventative obligations outlined in stormwater regulations. It also exposes the municipality to potential enforcement actions and fines. A third incorrect approach is to focus solely on the most visually obvious pollutant, such as trash, while neglecting other potentially more harmful pollutants like dissolved metals or nutrient runoff. This is a regulatory failure as it demonstrates an incomplete understanding of the diverse range of stormwater pollutants and their impacts. Ethically, it is a failure to provide comprehensive environmental protection, as less visible pollutants can have severe long-term consequences for aquatic ecosystems and human health. Professional reasoning. Professionals in stormwater management must adopt a systematic, evidence-based decision-making process. This involves 1. Understanding the regulatory requirements and their underlying environmental protection goals. 2. Conducting thorough site assessments and data collection to identify pollutant sources and transport mechanisms. 3. Evaluating potential remediation strategies based on their effectiveness, cost efficiency, and compliance with regulations. 4. Engaging stakeholders and communicating findings transparently. And 5. Implementing and monitoring chosen strategies to ensure ongoing compliance and environmental improvement. Ethical considerations, such as the duty to protect public health and the environment, must guide every step of this process, especially when faced with competing priorities. Question 12. Analysis of a certified stormwater manager's ethical obligations when a client proposes substituting a less effective, cheaper best management practice, BMP, for a regulatory required, more expensive BMP, citing budget constraints. The manager has confirmed the proposed BMP will not meet the required water quality performance standards. What is the most professionally responsible course of action? Option A. Inform the client that, while the proposed BMP is less effective, it is acceptable as long as the client signs a waiver acknowledging the reduced performance and potential risks. Option B. Implement the less effective BMP as requested by the client without further discussion, as the client ultimately controls project funding and decisions. Option C. Clearly explain to the client that the proposed BMP is not compliant with regulations and will not achieve the necessary water quality objectives, and therefore cannot be implemented. Offer to explore alternative, compliant BMPs that might be more cost-effective, or discuss phased implementation if feasible and permitted by regulations. Option D. Agree to the client's proposed BMP substitution to maintain a good client relationship and avoid project delays, assuming the environmental impact will be minimal. The correct answer is C. Clearly explain to the client that the proposed BMP is not compliant with regulations and will not achieve the necessary water quality objectives, and therefore cannot be implemented. Offer to explore alternative, compliant BMPs that might be more cost-effective, or discuss phased implementation if feasible and permitted by regulations. Explanation. Scenario analysis. This scenario presents a common ethical dilemma for a certified stormwater manager, where a client's desire for cost savings conflicts with the regulatory requirements for effective stormwater management. The challenge lies in balancing the client's financial interests with the professional and legal obligation to implement best management practices, BMP, that adequately protect water quality. The manager must navigate this tension while upholding professional integrity and ensuring compliance. Correct approach analysis. The correct approach involves clearly communicating the regulatory mandates and the scientific rationale behind the proposed BMPs. This demonstrates adherence to the certified stormwater manager's ethical code, which prioritizes environmental protection and regulatory compliance. By explaining that the chosen BMPs are not merely suggestions, but are required by law to achieve specific water quality objectives, the manager upholds their professional responsibility. This approach educates the client, fosters trust, and ensures that the project meets all legal and environmental standards, thereby preventing potential future liabilities for both the client and the manager. Incorrect approaches analysis. One incorrect approach involves agreeing to substitute a less effective BMP without proper technical justification or regulatory approval. This violates the fundamental principle of implementing BMPs that are designed to meet performance standards. Ethically, it represents a failure to act with due diligence and could lead to non-compliance with stormwater regulations, resulting in fines, legal action, and environmental damage. Another incorrect approach is to defer entirely to the client's preference for the cheapest option, regardless of its efficacy or regulatory compliance. This prioritizes financial gain over environmental responsibility and professional duty. It constitutes a breach of professional ethics by failing to provide expert guidance and by potentially enabling non-compliant practices. This can lead to significant legal repercussions and reputational damage. A third incorrect approach is to implement the less effective BMP without informing the client of the potential risks or regulatory non-compliance. This is deceptive and unethical. It fails to uphold the duty of transparency and honesty expected of a certified stormwater manager. The manager would be complicit in a potentially illegal and environmentally harmful action, exposing themselves and the client to severe penalties. Professional reasoning. Professionals should approach such situations by first thoroughly understanding the relevant stormwater regulations and the specific performance criteria for BMPs. They should then assess the proposed BMPs against these criteria and the site-specific conditions. When faced with client pressure for cost reduction, the professional's duty is to clearly articulate the regulatory requirements and the technical reasons for selecting specific BMPs. This involves presenting data, explaining potential consequences of non-compliance, and offering alternative compliance solutions if available. The decision-making process should always prioritize regulatory adherence and environmental protection, followed by a collaborative effort with the client to find cost-effective solutions that still meet these essential requirements. Question 13. The risk matrix shows a moderate likelihood of noncompliance with stormwater regulations due to an inaccurate watershed characterization for a proposed development. The project team has access to recent GIS data including digital elevation models, land use/land cover maps, and soil surveys. Which approach best addresses this risk while adhering to professional stormwater management standards? Option A. Prioritize the digital elevation model for watershed delineation and assume standard hydrologic soil groups based on general regional classifications. Option B. Utilize the soil survey data to identify hydrologic soil groups and then estimate impervious surfaces based on the proposed development's footprint without further site-specific verification. Option C. Conduct a comprehensive field verification of the GIS-derived watershed boundaries, land use, soil types, and impervious surfaces, integrating these findings with the GIS data to refine the characterization. Option D. Rely solely on the most recent land use/land cover GIS layer to define the watershed's characteristics, assuming it accurately reflects current site conditions. The correct answer is C. Conduct a comprehensive field verification of the GIS-derived watershed boundaries, land use, soil types, and impervious surfaces, integrating these findings with the GIS data to refine the characterization. Explanation. Scenario analysis. This scenario presents a common implementation challenge in stormwater management: the practical application of watershed delineation and characterization data in a real-world development project. The challenge lies in reconciling the theoretical precision of GIS-derived data with the dynamic and often imprecise nature of existing site conditions and the varying levels of detail available from different data sources. A certified stormwater manager must exercise professional judgment to ensure that the chosen approach is both regulatory compliant and practically effective for managing stormwater runoff. Correct approach analysis. The correct approach emphasizes the integration of multiple data sources and a field verification step. This aligns with best professional practice because it acknowledges that while GIS is a powerful tool, it is not infallible. Regulatory frameworks, such as those under the Clean Water Act, assuming U.S. jurisdiction for this exam, require accurate characterization of the receiving waters and the contributing watershed to inform effective stormwater pollution prevention plans, SWPPP, and post-construction stormwater management designs. Field verification ensures that the delineated boundaries and identified land uses accurately reflect the current site conditions, accounting for any unmapped features or changes that could impact runoff. This thoroughness is ethically imperative to protect water quality and prevent flooding. Incorrect approaches analysis. One incorrect approach might rely solely on readily available, but potentially outdated or generalized digital elevation models, DEM, without considering other contributing factors or performing field checks. This fails to meet regulatory requirements for accurate watershed characterization, as it may misrepresent drainage divides, underestimate contributing areas, or overlook critical land use features. Ethically, it represents a failure to exercise due diligence. Another incorrect approach could involve prioritizing the most recent land use data from a GIS layer without cross-referencing it with soil surveys or conducting site reconnaissance. This could lead to an inaccurate assessment of hydrologic soil groups and impervious surface areas, which are critical for calculating runoff volumes and designing appropriate BMPs. This approach risks noncompliance with regulations that mandate accurate hydrologic modeling. A third incorrect approach might focus exclusively on the topographic slope analysis from a DEM, neglecting the crucial role of soil types and their infiltration capacities. While slope influences flow velocity, it doesn't tell the whole story of how water will infiltrate or run off. This incomplete characterization can lead to the selection of ineffective BMPs, potentially violating permit conditions and failing to protect water quality. Professional reasoning. Professionals should adopt a systematic, multifaceted approach. Begin with GIS analysis for initial delineation and characterization. Critically evaluate the quality and recency of all data sources, DEM, land use, soil maps. Prioritize field verification to confirm boundaries, identify actual land cover, and assess soil conditions. Integrate all findings to create a comprehensive watershed characterization that meets regulatory standards and informs effective stormwater management strategies. This iterative process of data analysis, verification, and integration ensures both compliance and practical efficacy. Question 14. Cost-benefit analysis shows that implementing advanced low-impact development (LID) techniques to maximize infiltration and groundwater recharge during a new commercial development project will have higher upfront capital costs compared to traditional detention basin designs. However, these LID techniques are projected to significantly reduce the long-term need for downstream infrastructure upgrades and ongoing maintenance, while also improving the quality of groundwater. Considering the principles of the hydrologic cycle and the goals of stormwater management, which approach best balances economic considerations with environmental stewardship and regulatory compliance. Option A. Implement basic stormwater controls that meet minimum regulatory requirements but do not significantly enhance infiltration or groundwater recharge, as the cost-benefit analysis favors lower initial expenditure. Option B. Prioritize the implementation of LID techniques that enhance infiltration and groundwater recharge, recognizing the long-term economic and environmental benefits that outweigh the initial capital investment. Option C. Focus on minimizing on-site stormwater controls and instead invest in off-site mitigation projects to offset the increased runoff and pollutant loading from the development. Option D. Opt for traditional detention basin designs to minimize initial construction costs, relying on post-construction monitoring and adaptive management to address any unforeseen downstream impacts. The correct answer is B. Prioritize the implementation of LID techniques that enhance infiltration and groundwater recharge, recognizing the long-term economic and environmental benefits that outweigh the initial capital investment. Explanation: this scenario is professionally challenging because it requires balancing the immediate financial pressures of development with the long-term environmental and regulatory obligations related to stormwater management. The certified stormwater manager must navigate the complexities of the hydrologic cycle and its impact on water quality and quantity, ensuring compliance with the Clean Water Act and relevant state and local regulations. The core challenge lies in optimizing processes to achieve both economic viability and environmental protection, which often involves upfront investment for long-term gains. The correct approach represents best professional practice because it prioritizes a comprehensive understanding of the hydrologic cycle's components and their interrelationships. By focusing on infiltration and groundwater recharge through low-impact development (LID) techniques, it directly addresses the root causes of increased runoff volume and pollutant loading. This proactive strategy minimizes the need for costly end-of-pipe treatment and reduces the long-term burden of managing downstream impacts, aligning with the principles of sustainable development and regulatory intent to protect water bodies. It demonstrates a commitment to environmental stewardship and a forward-thinking approach to stormwater management that is both ecologically sound and economically prudent over the project's lifecycle. An incorrect approach that focuses solely on minimizing initial construction costs by implementing only basic, conventional stormwater controls, e.g., detention ponds without significant infiltration components, fails to adequately address the increased runoff volume and pollutant transport inherent in development. This approach is a regulatory failure because it likely falls short of meeting the total suspended solids, TSS, and other pollutant reduction targets mandated by the Clean Water Act and associated permits. Ethically, it represents a short-sighted decision that prioritizes immediate financial gain over the long-term health of receiving waters and the community's water resources. Another incorrect approach that relies heavily on post-construction monitoring and adaptive management as the primary strategy, without robust pre-construction design for infiltration, is also problematic. While adaptive management is a valuable tool, it should supplement, not replace, effective source control and infiltration design. This approach can be a regulatory failure if the initial design does not meet performance standards, leading to noncompliance and potential enforcement actions. Ethically, it shifts the burden of remediation to the future, potentially increasing costs and environmental damage if problems arise that are difficult or expensive to correct. A third incorrect approach that proposes to offset increased runoff through off-site mitigation without addressing on-site infiltration and source control is also professionally unsound. While off-site mitigation can be a component of a comprehensive plan, it does not fulfill the regulatory requirement to manage stormwater impacts at the source. This approach is a regulatory failure, as it bypasses the fundamental principles of stormwater management, which emphasize on-site controls and minimizing the hydrologic impact of development. Ethically, it can be seen as an attempt to circumvent direct responsibility for the environmental consequences of the development. The professional decision-making process for similar situations should involve a thorough site assessment, detailed understanding of the project's hydrologic impacts, and a comprehensive review of all applicable regulations. Professionals should prioritize strategies that mimic natural hydrologic processes, such as maximizing infiltration and evapotranspiration, before considering more conventional or off-site solutions. A robust cost-benefit analysis should consider not only initial capital costs, but also long-term maintenance, operational expenses, and the potential costs associated with non-compliance and environmental degradation. Engaging with regulatory agencies early in the design process is also crucial to ensure alignment and avoid costly redesigns. Question 15. Research into effective public education and outreach strategies for stormwater management, as mandated by the Certified Stormwater Manager (CSM) framework, has identified several potential approaches. Considering the CSM's emphasis on fostering community engagement and promoting responsible stormwater practices, which of the following approaches is most aligned with best professional practice and regulatory requirements? Option A. Developing a comprehensive outreach plan that includes tailored messaging for diverse community groups, utilizing a mix of digital platforms, community workshops, and partnerships with local organizations, with a focus on practical actions individuals can take. Option B. Creating generic public service announcements for broadcast media that cover broad environmental themes, without specific stormwater management actions or local relevance. Option C. Organizing a single, large-scale public event with guest speakers, without a clear follow-up strategy or ongoing communication channels. Option D. Disseminating technical reports and scientific data through official government websites, assuming the public will access and interpret this information independently. The correct answer is A. Developing a comprehensive outreach plan that includes tailored messaging for diverse community groups, utilizing a mix of digital platforms, community workshops, and partnerships with local organizations, with a focus on practical actions individuals can take. Explanation. This scenario is professionally challenging because it requires balancing diverse stakeholder interests and perceptions while adhering to the specific public education and outreach requirements mandated by the Certified Stormwater Manager (CSM) regulatory framework. Effective stormwater management relies heavily on public understanding and participation, making the communication strategy critical. The CSM framework emphasizes practical, actionable outreach that resonates with different community segments. The correct approach represents best professional practice because it directly addresses the core objectives of public education and outreach as defined by the CSM. It involves tailoring messages to specific audiences, utilizing a variety of communication channels to maximize reach and engagement, and providing clear, actionable information that empowers individuals to participate in stormwater management efforts. This aligns with the CSM's emphasis on fostering a sense of shared responsibility and promoting behavioral change through informed public action. The approach is proactive, inclusive, and evidence-based, ensuring that outreach efforts are both effective and compliant with regulatory intent. An incorrect approach that focuses solely on broad, generic public service announcements fails to meet the CSM's requirement for targeted and impactful education. This approach is ethically deficient because it wastes resources on potentially ineffective communication and fails to adequately inform or engage the public on specific stormwater issues relevant to their daily lives. It also risks alienating stakeholders who may feel their concerns are not being addressed. Another incorrect approach that prioritizes a single, high-profile event without follow-up or sustained engagement overlooks the CSM's emphasis on ongoing education and reinforcement. This is professionally unsound, as it creates a fleeting awareness rather than lasting behavioral change. Ethically, it can be seen as a superficial attempt to meet outreach requirements without genuine commitment to public understanding and participation. A third incorrect approach that relies exclusively on technical reports and scientific data, without translating this information into accessible language for the general public, is also professionally inadequate. While scientifically accurate, it fails the fundamental purpose of public education, which is to inform and motivate action. This approach is ethically problematic as it creates an information barrier, preventing the intended beneficiaries of stormwater management efforts from understanding their role and responsibilities. The professional decision-making process for similar situations should involve a thorough understanding of the specific CSM regulations regarding public education and outreach. This includes identifying target audiences, assessing their current knowledge and attitudes, and selecting communication methods that are most likely to achieve desired outcomes. Professionals should prioritize strategies that are inclusive, culturally sensitive, and provide clear, actionable guidance. Regular evaluation of outreach effectiveness and adaptation of strategies based on feedback and results are also crucial components of best professional practice. Question 16. The evaluation methodology shows that a recently installed silt fence on a construction site, designed to manage sediment runoff from a sloped area, is exhibiting significant sagging and sediment bypass after a moderate rainfall event. The site is subject to U.S. EPA regulations under the Clean Water Act and a state-issued general permit for stormwater discharges from construction activities. Considering the observed failure, which of the following actions best reflects professional stormwater management practice and regulatory compliance? Option A. Immediately inspect the silt fence for proper installation and anchoring, and if deficiencies are found, repair or replace it. If the installation appears correct, assess the need for additional sediment control measures such as straw wattles or inlet protection downstream, or consider upgrading to a more robust erosion control blanket given the slope and rainfall intensity. Option B. Focus on stabilizing the disturbed soil areas with vegetation or temporary cover, as this is the primary method for long-term erosion control, and the silt fence is a secondary measure. Option C. Immediately remove the silt fence and rely solely on the natural topography to manage sediment, as the fence has proven ineffective. Option D. Document the observed bypass but continue to monitor the silt fence, assuming it will perform adequately during future, less intense rainfall events. The correct answer is A. Immediately inspect the silt fence for proper installation and anchoring, and if deficiencies are found, repair or replace it. If the installation appears correct, assess the need for additional sediment control measures such as straw wattles or inlet protection downstream, or consider upgrading to a more robust erosion control blanket given the slope and rainfall intensity. Explanation. This scenario presents a common challenge for certified stormwater managers, balancing immediate site needs with long-term environmental protection under evolving site conditions. The professional challenge lies in accurately assessing the effectiveness of installed sediment control measures when faced with unexpected rainfall intensity and duration, and then making informed decisions about necessary upgrades or modifications. This requires not just knowledge of best management practices, BMP, but also an understanding of their limitations and the specific regulatory requirements for maintaining compliance. The correct approach represents best professional practice because it prioritizes proactive assessment and adaptive management in response to observed performance and potential regulatory noncompliance. By recognizing that the existing silt fence is failing to adequately contain sediment, the manager is demonstrating due diligence and adherence to the principles of the Clean Water Act, CWA, and relevant state/local stormwater pollution prevention program, SWPPP, requirements. This proactive stance aims to prevent sediment from reaching receiving waters, which is a primary objective of stormwater regulations. It also aligns with the ethical responsibility to protect water quality and avoid environmental harm. An incorrect approach that relies solely on the initial installation of a silt fence, despite visible signs of failure, represents a regulatory failure. Regulations typically require that BMPs be maintained in effective operating condition. Ignoring evidence of failure means the site is likely not in compliance with its SWPPP and the CWA. Ethically, this demonstrates a lack of commitment to environmental protection and a failure to uphold professional standards. Another incorrect approach that involves simply adding more silt fence material without addressing the underlying cause of failure e.g., improper installation, inadequate anchoring, or overwhelming flow is also professionally unacceptable. This is a superficial fix that does not guarantee effectiveness and may lead to continued noncompliance. It fails to address the root problem and demonstrates a lack of analytical rigor in diagnosing the issue. A further incorrect approach that involves waiting for a formal notice of violation before taking action is a critical regulatory and ethical failure. Professional stormwater managers are expected to be proactive in identifying and rectifying compliance issues. Waiting for enforcement action indicates a reactive and potentially negligent approach, which can result in significant penalties and environmental damage. The professional decision-making process for similar situations should involve a systematic evaluation. 1. Observe and document the performance of existing BMPs. 2. Compare observed performance against regulatory requirements and design specifications. 3. Identify the root cause of any observed deficiencies. 4. Determine the most effective corrective actions, considering site-specific conditions and regulatory mandates. 5. Implement corrective actions promptly and document all steps taken. 6. Reevaluate the effectiveness of the corrective actions. This structured approach ensures that decisions are data-driven, compliant, and ethically sound, prioritizing the protection of water resources. Question 17. The performance metrics show a consistent trend of increased stormwater runoff volume and pollutant loading in a rapidly developing urban area. Considering the need for a sustainable and compliant stormwater management program, which of the following approaches best aligns with the principles of a comprehensive stormwater master plan, infrastructure assessment, capital improvement planning, and funding strategies? Option A. Creating a stormwater management plan that primarily addresses aesthetic improvements and green space integration, with minimal emphasis on the assessment of critical infrastructure capacity and the establishment of robust funding mechanisms for essential upgrades. Option B. Implementing a reactive maintenance schedule for existing infrastructure and requiring new developments to incorporate basic best management practices, BMP, without a comprehensive assessment of the entire watershed's needs or a long-term funding plan. Option C. Developing a phased capital improvement plan that prioritizes infrastructure upgrades based on a detailed assessment of existing conditions and projected impacts, supported by a diversified funding strategy, including dedicated stormwater utility fees and impact fees, all guided by a comprehensive stormwater management plan that sets clear performance objectives and regulatory compliance targets. Option D. Focusing exclusively on retrofitting older, non-compliant infrastructure, while deferring upgrades to newer systems and neglecting the development of a stable, long-term funding mechanism beyond annual budget allocations. The correct answer is C. Developing a phased capital improvement plan that prioritizes infrastructure upgrades based on a detailed assessment of existing conditions and projected impacts, supported by a diversified funding strategy, including dedicated stormwater utility fees and impact fees, all guided by a comprehensive stormwater management plan that sets clear performance objectives and regulatory compliance targets. Explanation: the performance metrics show a consistent trend of increased stormwater runoff volume and pollutant loading in a rapidly developing urban area. This scenario is professionally challenging because it requires a proactive and comprehensive approach to stormwater management that goes beyond reactive problem solving. The challenge lies in balancing the need for continued urban growth with the imperative to protect water quality and mitigate flood risks, all while operating within the constraints of existing regulatory frameworks and limited financial resources. A robust stormwater master plan is essential to address these interconnected issues effectively. The correct approach represents best professional practice because it prioritizes a data-driven, integrated, and long-term strategy for stormwater management. This involves a thorough infrastructure assessment to understand the current state of the system, a comprehensive stormwater management plan that outlines specific goals and strategies aligned with regulatory requirements, e.g., Clean Water Act, NPDES permits, and a capital improvement plan that strategically prioritizes projects based on effectiveness and urgency. Crucially, it includes the development of diverse and sustainable funding strategies to ensure the long-term viability of these initiatives. This holistic approach ensures compliance with regulations, promotes environmental stewardship, and builds community resilience. An incorrect approach that focuses solely on reactive maintenance without a master plan fails to address the root causes of increasing runoff and pollution, leading to continued environmental degradation and potential noncompliance with regulatory discharge limits. This approach is ethically questionable as it neglects the responsibility to protect public health and the environment. Another incorrect approach that prioritizes only new development controls without assessing existing infrastructure ignores the significant contribution of legacy development to the overall stormwater problem. This leads to an incomplete and ineffective management strategy, potentially violating the spirit and letter of regulations that require comprehensive watershed management. A third incorrect approach that relies on a single, unsustainable funding source, such as ad hoc grants, is professionally unsound. It creates uncertainty and jeopardizes the long-term implementation and maintenance of critical stormwater infrastructure, potentially leading to system failures and regulatory violations. This demonstrates a lack of foresight and commitment to sustainable stormwater management. The professional decision-making process for similar situations should involve 1. Understanding the regulatory landscape and compliance obligations. 2. Conducting a thorough assessment of existing conditions and future projections. 3. Developing a comprehensive plan that integrates infrastructure, management practices, and funding. 4. Engaging stakeholders to build consensus and secure support. 5. Continuously monitoring performance and adapting strategies as needed. Question 18. Which approach would be most appropriate for developing a defensible hydrologic and hydraulic model to support a new stormwater management plan submission under the Clean Water Act, given the availability of local historical rainfall data and some limited stream gauge flow data for the project area? Option A. Proceed with model development using only the local rainfall data, but skip the calibration and validation steps, assuming the model's default parameters are sufficiently accurate for regulatory purposes. Option B. Employ a generic pre-existing model template for a similar watershed type and assume standard runoff coefficients and infiltration rates without incorporating specific local rainfall or flow data, as this will expedite the submission process. Option C. Select a complex, advanced modeling software and input only generalized regional climate data, bypassing the use of specific local rainfall and stream gauge data to simplify the modeling process. Option D. Utilize a widely accepted modeling software such as SWMM, incorporating the local historical rainfall data as input, and then calibrate and validate the model using the available stream gauge flow data to ensure it accurately represents the watershed's response to rainfall events. The correct answer is D. Utilize a widely accepted modeling software such as SWMM, incorporating the local historical rainfall data as input, and then calibrate and validate the model using the available stream gauge flow data to ensure it accurately represents the watershed's response to rainfall events. Explanation. This scenario presents a common challenge in stormwater management, ensuring that a hydrologic and hydraulic H&H model accurately reflects real-world conditions for effective regulatory compliance and infrastructure design. The challenge lies in balancing the need for a robust, defensible model with the practical constraints of data availability and project timelines. Professional judgment is crucial in selecting the most appropriate modeling approach to meet the specific objectives of the stormwater management plan. The correct approach represents best professional practice because it directly addresses the core requirements of regulatory frameworks for stormwater management. By utilizing a widely accepted software like SWMM, incorporating relevant local rainfall data, and performing calibration and validation against observed flow data, the model becomes a reliable tool for predicting stormwater behavior. This process ensures that the model's outputs are scientifically sound and can be used to demonstrate compliance with permit requirements and design standards. The iterative nature of calibration and validation, involving adjustments based on observed data, is a fundamental tenet of good H&H modeling, leading to a more accurate representation of the system's response. An incorrect approach that relies solely on default parameters without local calibration fails to meet regulatory expectations for site-specific analysis. Regulations typically require models to be representative of the actual conditions of the site and its contributing watershed. Using generic or assumed values, rather than calibrating to local rainfall runoff relationships, introduces significant uncertainty and can lead to inaccurate predictions of peak flows, volumes, and inundation extents. This undermines the purpose of the model, which is to inform decisions about stormwater control measures and flood mitigation, potentially resulting in underdesigned or overdesigned systems and noncompliance with environmental protection goals. Another incorrect approach that bypasses validation against observed data is also professionally unacceptable. Validation is a critical step that confirms the calibrated model's ability to accurately predict conditions beyond the calibration period or for different storm events. Without validation, the model's predictive capability remains unproven, making its results unreliable for decision-making. This can lead to a false sense of confidence in the model's accuracy, potentially resulting in inadequate stormwater management strategies that fail to protect water quality or prevent flooding, thereby violating the intent of stormwater regulations. The professional reasoning process for similar situations should involve a thorough understanding of the project's objectives, the specific regulatory requirements, and the available data. A systematic approach should be adopted. First, select appropriate modeling software based on the complexity of the system and regulatory acceptance. Second, gather and process all relevant input data, prioritizing local and site-specific information. Third, perform rigorous calibration using historical storm events and observed data. Fourth, validate the calibrated model against independent data. And finally, conduct scenario analysis to evaluate the effectiveness of proposed management strategies and demonstrate compliance. This structured process ensures that the modeling effort is scientifically sound, defensible, and effectively supports the goals of stormwater management. Question 19. The review process indicates that a stormwater management plan relies on a water quality modeling approach that uses generalized, regional pollutant loading rates and a simplified BMP effectiveness factor without site-specific calibration or validation. The plan then extrapolates these results to predict receiving water impacts. Which of the following modeling approaches best aligns with the principles of robust water quality assessment and regulatory compliance for a certified stormwater manager? Option A. Utilizing a generic pollutant loading calculator that assumes average urban runoff characteristics and applying a standard percentage reduction for all BMP types, without considering the specific design or maintenance of the BMPs or the characteristics of the receiving water. Option B. Adapting a groundwater contamination model to estimate surface runoff pollutant concentrations, without accounting for the unique transport mechanisms and temporal dynamics of stormwater events. Option C. Employing a calibrated and validated hydrological and water quality model that simulates site-specific pollutant generation based on land use, soil types, and precipitation data, and then models the performance of selected BMPs using established or site-specific effectiveness data, followed by an assessment of the predicted pollutant loads on the designated receiving water body. Option D. Focusing solely on the hydraulic performance of BMPs, such as infiltration rates and storage volumes, and assuming that improved hydrology will automatically lead to acceptable water quality in the receiving waters. The correct answer is C. Employing a calibrated and validated hydrological and water quality model that simulates site-specific pollutant generation based on land use, soil types, and precipitation data, and then models the performance of selected BMPs using established or site-specific effectiveness data, followed by an assessment of the predicted pollutant loads on the designated receiving water body. Explanation: this scenario is professionally challenging because it requires a nuanced understanding of how different approaches to water quality modeling can lead to significantly different conclusions about the effectiveness of stormwater management practices, BMP, and their impact on receiving waters. The challenge lies in selecting the most appropriate modeling methodology that aligns with regulatory expectations and provides a defensible assessment of pollutant load reductions and potential water quality degradation. The correct approach represents best professional practice because it prioritizes a comprehensive and scientifically sound methodology that directly addresses the regulatory objectives of the Certified Stormwater Manager exam. This involves selecting a model that can accurately simulate pollutant generation, transport, and the effectiveness of specific BMPs under relevant hydrological and meteorological conditions. Furthermore, it emphasizes the critical step of assessing the impact on receiving waters, which is a core requirement for demonstrating compliance and protecting aquatic ecosystems. This approach ensures that the modeling results are not only technically sound, but also directly applicable to regulatory decision-making and the development of effective stormwater management plans. An incorrect approach that relies solely on simplified, generalized pollutant loading factors without accounting for site-specific conditions or BMP performance would be professionally unacceptable. This fails to meet the regulatory requirement for a detailed and accurate assessment, potentially leading to an underestimation of pollutant loads or an overestimation of BMP effectiveness. Ethically, this approach misrepresents the actual environmental impact and could result in inadequate protection of receiving waters. Another incorrect approach that focuses exclusively on modeling BMP effectiveness without a robust pollutant load calculation or a thorough receiving water impact assessment is also professionally flawed. While BMP effectiveness is important, it must be evaluated within the context of the pollutants being managed and their ultimate fate in the receiving environment. This approach neglects the critical upstream and downstream components of the water quality assessment, leading to an incomplete and potentially misleading analysis. A third incorrect approach that uses a model designed for a different type of environmental assessment, such as groundwater contamination, and attempts to adapt it for stormwater runoff and receiving water quality, would be a significant regulatory and ethical failure. This demonstrates a lack of understanding of the specific modeling requirements for stormwater management and a disregard for the scientific principles necessary for accurate assessment. It would likely produce unreliable results and undermine the credibility of the stormwater management plan. The professional reasoning process for similar situations should involve 1. Clearly defining the regulatory objectives and the scope of the assessment. 2. Identifying the specific pollutants of concern and the relevant receiving water bodies. 3. Evaluating available modeling tools and methodologies based on their ability to accurately represent site-specific conditions, pollutant sources, BMP performance, and receiving water dynamics. 4. Selecting the most appropriate model and data inputs that are defensible and meet regulatory standards. 5. Critically interpreting the model outputs and assessing their implications for water quality protection and compliance. 6. Documenting the modeling process and assumptions thoroughly to ensure transparency and defensibility. Question 20. The analysis reveals that a new commercial development project is proposed in a municipality that has adopted its own stormwater management ordinance, which includes specific requirements for post-construction infiltration rates that are more stringent than the state's minimum standards. The project's stormwater management plan has been designed to meet the state's requirements. What is the most appropriate course of action for the certified stormwater manager overseeing this project? Option A. Proceed with the stormwater management plan as designed, as it meets the state's minimum requirements, and assume the local ordinance will not be strictly enforced in this instance. Option B. Focus solely on meeting the state's stormwater regulations, as these are generally considered the primary legal authority for stormwater management across the jurisdiction. Option C. Submit the stormwater management plan to the state environmental agency for approval, and then inform the local municipality that the state has approved the plan, implying it should be accepted. Option D. Revise the stormwater management plan to meet the more stringent infiltration rate requirements stipulated in the local municipal ordinance, in addition to the state's minimum standards. The correct answer is D. Revise the stormwater management plan to meet the more stringent infiltration rate requirements stipulated in the local municipal ordinance, in addition to the state's minimum standards. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a stormwater manager to navigate a complex web of overlapping regulatory requirements at both the state and local levels. The challenge lies in identifying which regulations take precedence, understanding the nuances of local ordinances that may be more stringent than state mandates, and ensuring compliance with development standards that are often specific to individual municipalities. Failure to accurately interpret and apply these layered regulations can lead to significant enforcement actions, project delays, and reputational damage. Correct approach analysis. The correct approach involves a thorough review and synthesis of both state-specific stormwater regulations and the relevant local ordinances and codes. This includes understanding the minimum requirements set by the state, and then identifying any local provisions that impose stricter standards or additional requirements, such as specific development standards for infiltration, buffer zones, or post-construction monitoring. Best professional practice dictates prioritizing the most stringent applicable requirement to ensure full compliance and to proactively address potential enforcement issues. This approach demonstrates a commitment to environmental protection and adherence to the legal framework governing stormwater management. Incorrect approaches analysis. One incorrect approach is to solely rely on state-level regulations, assuming they represent the entirety of compliance obligations. This fails to acknowledge the authority of local governments to enact more protective measures through their ordinances and codes. Such an approach risks violating local requirements, leading to fines, stop work orders, and legal challenges. Another incorrect approach is to focus exclusively on local ordinances without considering the overarching state framework. While local rules may be stricter, they must still operate within the bounds of state law. Ignoring state mandates could result in noncompliance with broader environmental protection goals and potential state-level enforcement actions. A third incorrect approach is to assume that standard development practices are universally accepted and compliant without verifying them against specific state and local stormwater regulations. Development standards are often tailored to local environmental conditions, soil types, and hydrological characteristics, and deviations without proper justification and approval can lead to non-compliance and environmental harm. Professional reasoning. Professionals should adopt a hierarchical approach to regulatory review. First, identify all applicable state stormwater regulations. Second, identify all relevant local ordinances, codes, and development standards within the project's jurisdiction. Third, compare the requirements from both levels, always applying the most stringent standard. This systematic process ensures that all legal obligations are met and that the project adheres to the highest level of environmental protection mandated by the governing authorities. Regular consultation with local planning and environmental departments is also crucial for staying abreast of any amendments or interpretations of these regulations.